Z-scores. Our objective, determine and interpret what are called Z-scores. So let's remind ourselves what we know. We know what standard deviation is. It is how far on average each observation is from the mean. Okay? We're going to make use of that right now. Okay, so let's take a look at an example. Well, let's first define a z-score and what's involved with a z-score. Z-score, the distance that a data value is from the mean in terms of how many standard deviations. Okay, it's one thing to say this value is 25 units, let's say minutes, away from the mean. It's another thing to say that this data value is 1.5 standard deviations away from the mean. Okay, one of them is unit specific. The other one has been standardized a little bit, okay? So we're measuring a data item's position relative to the mean in a bell-shaped distribution. Okay, again, we're talking about normal distributions, bell-shaped, normal that we're working with. Normal data, not skewed data, normal data. The z-score is calculated. It's the data item minus the mean divided by the standard deviation. We're going to do that in our example in just a moment. Positive z-scores mean that we are above the mean. We're to the right of the mean, to the right being above. Negative z-scores indicate values that are below the mean, to the left of the mean. We saw that in a previous lecture. Z-scores standardize bell-shaped data sets, okay? This, therefore, allows for the comparison of scores that are from different distributions. So z-scores transform the variable x with a mean of mu. So you have a variable, with a mean of mu and a standard deviation of sigma, into a random variable with a mean of 0 and a standard deviation of 1 so that we can compare them. And you'll see that in a couple of cases here. We'll do that twice. Okay, let's do our first example here. Let me keep that z-score formula in the view for you. Which baseball team had a better run-producing season? The Red Sox or the Dodgers? Now, as some of you may know, if you're not a baseball fan, I'm not really a baseball fan, but I know this. The Red Sox are in the American League, in which the pitcher does not bat. Pitchers are generally not good hitters. And so removing the pitcher from the lineup means you're going to probably have more runs scored. The Dodgers are in the National League. The pitcher does bat. And because the pitcher generally is not a very good batter, you tend to have fewer runs scored because the pitcher is involved in the lineup. So, Red Sox are in the American League. The Red Sox scored 876 runs in the American League. The mean is 731.2 runs. The standard deviation is 72.6 runs. The Dodgers are in the National League. The pitcher bats. Therefore, they wound up scoring fewer runs, 804 runs. But it's in the National League where the mean is 710.8 runs, fewer than the American League. And the standard deviation is a little bit lower. It's a fair piece lower, actually, at 60.2 runs. Okay, so let's take a look let's calculate their z-scores so that we can compare them. Okay, the Red Sox. Okay, so we can't compare them data to data because in the American League, the pitcher plays and in the American League, the pitcher does not hit, and that results in more runs for American League teams. In the National League, the pitcher does hit, and that results in fewer runs for the National League teams. So we can't just compare them because they're different situations. But if we standardize the data using z-scores, we can compare them. So the Red Sox, what is their z-score? Z-score, the data item minus the mean divided by the standard deviation. Red Sox, 876 minus the mean, 731.2, divided by the standard deviation, 72.6. If I do the math, I get a Z-score of 1.99. The Red Sox are 1.99 standard deviations above the mean for the American League. Okay? Let's draw a bell curve. I'm going to try to do this as accurately as I can. There's the left side. Wow, should be symmetrical. And close enough. Okay, here is our mean. Okay, here is +1 standard deviation. Here is +2 standard deviations. The Red Sox are 1.99 standard deviations above the mean. Okay, well that means the Red Sox are essentially right there. Okay? For the, whoops, you couldn't see any of that. I'm sorry about that. I get myself caught up and look at what I'm doing. I drew a bell curve. I put the mean in here. My bell curve should be symmetrical. I labeled the mean. I went up 1 standard deviation, then a 2nd standard deviation. The Red Sox Z-score is 1.99. That's almost 2. So they are just about 2 standard deviations above the mean. And so I put the Red Sox at just about 2 standard deviations above the mean. Okay, there's the Red Sox. Now let's do the Dodgers. Okay, what is the Dodgers Z-score, which takes into account their different mean and standard deviation? And I can't spell score at the moment. S-C-O-R-E. Okay, data item for this Dodgers is 804. 804 runs for the Dodgers, minus the mean of the National League, 710.8, divided by the National League standard deviation of 60.2. We do the math with the calculator, we come up with 1.55. So with the National League, the Dodgers are 1.55 standard deviations above the mean in the National League. Down here, 1.55 puts them about here. This is the Dodgers. Okay, so now we can compare them. We can see that the Red Sox are further above the mean for their league than the Dodgers are for their league. So, which team had the better run-producing season? The Red Sox. They were further above the mean as compared to their league versus the Dodgers, who were not as far above the mean in comparison to their league. So we took these two different situations. We were able to standardize it using Z-scores, and then we could compare them and say, you know, when it comes to who has the better producing season, it was the Red Sox. They were further above their league's mean than the Dodgers were. Let's look at another example. Just a moment. It kind of goes, I shouldn't say the other direction, but let's take a look at kind of below the mean and how this might, the higher is not always better. How about that? We'll see that here. Okay. Bob and Mary ran a marathon. Bob's finishing time was 213 minutes. I probably should have put minutes there. Yeah, 213 minutes, where the mean finishing time among men was 242, and the standard deviation is 57 minutes. So Bob was obviously faster than the average male on the marathon. He did pretty well. Mary finished in 241 minutes, but she was slower than Bob, of course. But she's a woman, different category. In the women's division, the mean finishing time was 273 minutes with a standard deviation of 52 minutes. Who had the better time within their group, right? We're talking men versus women, who was better within their category. We can't compare them directly because they have different, they're different. Men and women aren't the same. But we can standardize them with the Z-score and speak to how good they were within their category, men or women. Okay, let's look at Bob. And let's do his Z-score. His Z-score, well, his data, he was 213 minutes. We're going to subtract the mean for men of 242 minutes. We're going to divide by the standard deviation for men, which is 57. And Bob was if I do the math, I get a negative 0.51. He was below, the negative is below, the mean by 0.51 standard deviations. Okay, let's take a look. Let's see if I can, let me get so you can see the picture. Okay, so here is my bell curve, kinda. That's pretty good. Here's the mean. Okay, mean. And now here is -1 standard deviation. Here is -2 standard deviations because we're below. Bob was 0.51 standard deviations below the mean. So where's Bob? 0.51 is right there. There's Bob. Okay, compared to the men's mean, Bob was faster. And when it comes to standard deviations, he's 0.51 standard deviations faster than the mean. Okay, that's Bob. Now let's take a look at Mary. How did she do in comparison to the women? Okay, so Mary, her Z-score. Again, this is allowing us to compare these two different categories. Okay, men versus women. And the previous example, we did American League versus National League. Okay, Mary's time was 241 minutes. We're going to subtract the mean time for women, which was 273. We're going to divide that by the standard deviation for women, which is 52. And we're going to come up with a negative 0.62. Okay, so she was below the average time for women by 0.62 standard deviations. Well, here's one. So Mary, approximately here. There's Mary. She was below the mean by 0.62 standard deviations. Bob was below the mean by 0.51 standard deviations. Okay? Whose time was better? We already know, Bob's time was faster, but that's because men tend to be faster than women, not a particularly fair comparison. But Mary's time, when you compare them within their categories, Mary's time was better because she was further below the mean. She was faster than Bob was. So let's just make a note of that. Mary's time is further below. In this case, that means faster. When you're below the mean in time, you're faster than the mean. Okay, therefore, she has the better time. Her time is better. There you go. So there's an example where being below the mean, you're looking at how much further below the mean. In this case, with time, the greater you are further below the mean, the better it is. So there you have it. A little bit of a look at Z-scores, so you can compare data from different categories by standardizing.